circle. And then you pick a random number, okay, and we'll just choose something nice to start with, so 10, okay? So then with 10, we put 10 points on the perimeter here, equally spaced. And then we label them with 1, 2, 3, 4, 5, 6, 7. Okay, let's just go. Actually, we start with 0. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then 10 we also want. So we kind of put that right there again. So that's also 10, that's also 11, 12, 13, 14, 15, and so on. Okay? And then again, and so on. Right? So this guy here stands for 1, 11, 21, 31, and so on. Okay? And now we're going to do the 2 times table. Okay, so 2 times table. And we'll start with 0. So 2 times 0 is?
0.
So 0 is the same thing, so we don't do anything. Okay, 2 times 1 is?
2.
2. Okay, so we connect the 1 to the 2. Then 2 times 2 is?
4.
Okay, so we do this and we keep on going. Pretty obvious. Now 5. 2 times 5 is?
10.
10. 10, remember? 10 is also over there, so we connect that guy up. And then 2 times 6 is 12, which is also the 2. So we connect that one, and you kind of just keep on going like this. Okay? And then you're at 9, and you've pretty much gone all the way around. Now you could go on. So for example, we could now do 2 times 10, and 2 times 11, and 2 times 12, and draw in those connections. But actually, the connections are going to be exactly the ones that we've already drawn. So we can actually stop here. Just to illustrate, let's just go up to 2. 2 times 12 is?
24.
24, which corresponds to the 4, and that connection's already there, right? And 2 times 13 is?
36.
Not quite.
2 times, sorry, what?
2 times 13.
2 times 13, 26.
26, and we've already got the 6. Of course, we made a choice there at the beginning, that 10, right? If you change that 10 to anything else, well, the picture changes, but pretty much everything I said stays the same, okay? So for example, if you switch from 10 to 11, we get this guy here, you know, and then 12, 13, 14, 15, and let's just see what happens.
So,
pretty nice.
Quick question.
Yeah.
All these pictures that you're showing, it seems that they are symmetric.
Yep.
In the horizontal axis. Like
That's right.
mirror.
Yep.
Is that for a particular reason?
Yep, there's a reason, and actually let's just give this as homework for our guys here to figure out. So in the comments, tell us why there's a symmetry. Of course, what's much more interesting here is that curve that somehow magically materializes when you kind of up the number that you choose at the beginning. Okay, and actually I'll just highlight it a bit. So there's this strange curve here. It's actually got a name. It pops up all over mathematics. It's called a cardioid. Like in cardiology, it means heart. Okay, so it's like a heart curve, mathematical heart curve. And it comes up in all kinds of places, and I'll just show you a few. Okay, so for example, you can have it as a rolling curve. You roll one circle around another circle, and just see what happens to one of the points on the boundary of the rolling circle. Okay, so for example here. And what it does is it traces the cardioid, okay? Now where else can you see it? Well, sometimes you can see it in your coffee cup. If it's in the direction of one of those green lines in the coffee cup, then you can also see a cardioid in there. Where else? Well, there, right there in the Mandelbrot set. So the biggest bulb in the Mandelbrot set is a cardioid. The second one is actually a perfect circle. Now, this would be a good one to figure out why is this guy a cardioid? And so just to kind of trace this down somewhere. Now, just for those people who know something about this stuff, that's the equation that we use to make up the Mandelbrot set, and there's a 2 in there. Okay, so that's important. We just had the 2 times table. So